Do one last example of the heated plate problem, which is a partial differential equation, in fact, the Laplace equation, boundary value problem. We've gone through two of these examples so far. Now we'll do the third. That will be the last one I show. Instead of these boundary conditions, oops, I want to do this on full screen. There we go. Let's see. In this third example, it's not going to be exactly like this. On the left and right, instead of the derivatives being zero, the temperature itself is. And along, I believe, the bottom, where y equals zero, it's the derivative is zero. It's insulated along the bottom in that case. Then I think it has some given function along the top. Let's see. Well, it's the same equation, the same Laplace equation. But with these different boundary conditions. And each side of x on the left, x on the right, the temperature itself is zero. On the bottom, where y equals zero, the temperature, or the derivative of the temperature is zero, meaning it's insulated down there. And at the top, it's some given function of x. When we do the product method, we've already gone through this twice or more. Get these two ordinary differential equations when the separation constant was minus lambda. And we have two boundary conditions of zero on the x guy. So we can completely solve for big X. That was case A. We don't want to keep redoing the same eigenvalue problem. So we just go to a formula sheet or our previous notes. Here's the eigenvalues and here's the eigenfunction. We use the same eigenvalues, same lambda y equation. So we're going to have since this is positive, we're going to have a quotient sinh solution for y. So there's what y is. Oh, because of this boundary condition, that leads us to, this is use y is xy prime, and 0 and y is 0. That means y prime at 0 is 0. So let's look at y prime. Here's what y is. Here's what y prime is. When the argument is 0, sinh is 0, cosh is 1. So I'm just left with n pi over ab. And it says that is 0. That means b equals 0. So the y's are just this part. Here's the y functions corresponding to all the same eigenvalues as these guys, as the x. So the total solution is those two guys multiplied, the product of those two guys, add them up in an infinite linear combination. Here is the general solution. It solves for the equation itself and these three boundary conditions. This is the only thing left. So what happens when I plug in b for y? I'm just plugging in b here, right? So that's the solution where y equals b, and that has to equal the function they told us about. We expand that function in a sine series, and we have a formula for that. By matching coefficients, all this stuff in front of the sine must equal this coefficients of the sine series. So this must equal that little a sub n, which has this formula. We have a formula for a sub n. So now we're done. Here's the general solution for u, and here's what those big a sub n's are. I could write it either way. Cosh is in the bottom, so I could write it as a hyperbolic c. That's the last example. One more thing to talk about. All our examples, we had zeros somewhere along the side. Either the temperature itself or the derivative of the temperature was zero. So we could completely solve for one of the two ordinary differential equations. What if it's function, some function on all four sides? Nothing's just zero, it's just some function around. Well, without going through this in detail, I can solve two different problems. Same Laplace equation for both problems. In one, I set for the x, and x equals 0 and x equal a, I'll set them to 0. And then for the other guys, I'll set it to the given boundary conditions in the real problem. And for the second problem, I'll set for the y extent, where y equals 0 and y equals b, I'll set those to 0. And then for the x ends, I'll use the given functions. If you go through the solutions you're going to get solutions for the first problem and the second problem. Remember, the overall solution is a sum of the individual solutions, and satisfy yourself that all the boundary conditions are also satisfied. So we use superposition to do that. In effect, each of these two problems you could do like we've already done. So you could do this whole problem. It's kind of like solving this similar problems twice. It's more tedious. In theory, you could do it. And that ends the Laplace equation, the heated plate, and the three sort of classic, easy partial differential equation bounding value problems.